So last time we studied about LU factorization, and then now we will skip the chapter 2.6 and 7 and then move to 2.8, which is about the subspace. Okay, so yeah, let's discuss about the definition of the subspace. So subspace is basically the subset of a fixed dimensional space. Yeah, for example, Rn. So the subspace should satisfy the following conditions. So given this Rn, a subset of these vectors in Rn, in order for it to be a subspace, it should satisfy that it has to contain the zero vector, and yeah, for the second and the third condition, it basically is equivalent to the fact that this subspace should be closed under the linear combination. Okay, so closed under addition and the scalar multiplication, so that is like linear combination. Okay, so what I mean by that is, so basically it's a subset of Rn. So let's say n is maybe 3, and then it basically has to contain zero vector by the first condition, and then suppose it contains maybe 1, 2, 3, okay, and then maybe 2, 3, 4, okay, and then this subset of the vectors should be closed under the linear combination, which means that you basically pick up or choose any of the two vectors in your set or subset of Rn, and then you freely generate a linear combination of the two chosen vectors. So one linear combination could be 1, 2, 3 and 2, 3, 4. Okay, so by just setting the linear combination coefficient as 1s for each of these vectors, and then we will obtain 3, 5, 7, right? And then this vector should also be included in the subset. Okay, so that's the meaning of this closedness. Okay, and also it has to contain 3, 5, 7 as well. And then maybe you have to you can set any other linear combinations like these, and then the resulting vector should also be contained in our subset of the vectors, so that it can be a subspace. Okay, so this closedness is a kind of some simple notion that we already studied in our middle school or high school. So for example, suppose we consider the set of the natural numbers, all the natural numbers, okay, and then maybe some set of the entire integers, and then maybe some real numbers, okay. And in this case, so we can consider some operations like this, okay, and then we studied whether each of these sets is closed under these operations. So for example, is this natural numbers, the set of natural numbers, closed under addition or not? It is closed because you just freely choose any of the two elements in this set, and then you perform this operation, and then if that element or that result is always included in the original set. So that's the meaning of this closedness. Okay, so it is closed. What about the subtraction? Is it? It is not closed because, for example, 3 minus 7, which is negative 4, is not closed, right? But in the case of integers, the set of entire integers, they are closed under this subtraction, right? But what about the multiplication? For this natural numbers, is it closed? It is closed, right? And it is closed, right? But what about these? So it is not, right? So we studied these kind of things, right, back in our high schools or middle school. So yeah, that closeness is applied to the operation of linear combinations when considering the set of some vectors. Okay, so if this set is closed under this linear combinations, and then this set is called subspace. Okay, not just a subset of the vectors, but a subspace. Okay, but still, again, n is fixed as a particular number. Okay. Right, and then this subspace, which we newly studied just now, is exactly the same as what we already studied, which is this span. Okay, so any subspace that satisfies this closeness under the linear combination, okay, that subspace should always be represented as the span of some finite number of vectors. Okay, so span is the subspace. Okay. So for example, consider this span of these two vectors v1 and v2, and then all the possible the collection of all the possible linear combinations is the definition of this span, right? So in this case, the plane that we see over here is corresponding to the span of v1 and v2, and then so let's consider whether this span is closed under the linear combinations. Okay, so let's suppose we choose any of the two vectors from here, and then each of these two vectors, so let's say the first vector is maybe 2v1 and 3v2, and x2, which is this guy, is maybe 4v1 and minus maybe 5v2. Okay, so these are just an example which are represented as a linear combination of v1 and v2, because that's the definition of the span. Any point or vector in the span should be represented as a linear combination of these v1 and v2. Okay, and then we consider their linear combination, right? Linear combination. So maybe 6x1 plus maybe 7x2. That is one particular linear combination using x1 and x2. And by the way, you can freely choose those linear combination coefficients as well for any numbers. Okay, but this is just one example. And then 6 times 2v1 and 3v2 plus 7 times 4v1 minus 5v2. Okay, and in this case 40v1 17, right? So it will be anyways represented as a linear combination of v1 and v2, which is included in the span, right? So we can easily see that it is closed under the linear combinations. Okay, so we easily saw that span of some particular vectors is satisfying the condition of this subspace, which is closed under the linear combination. But although we do not prove it rigorously, but yeah, any of the subspace that is closed under this linear combination will always be represented as a span of a finite number of vectors. Okay, so you can just intuitively you can just think of the subspace being the same as the span. Okay, but here here we will see kind of a different starting point, although the notion, the basic meaning between the subspace and the span are exactly the same. But in the case of span, we will always start with the v1 and v2 as a particular vectors that forms our span when considering the span at the beginning. But when considering a subspace, and then we are just given that kind of particular plane, and then what will this subspace, which is represented as a plane, represented as a span of some vectors. So what will be those vectors that will be the span of when spanning using that vectors, these span will be equivalent to this given subspace. So the starting point is this subspace, which is a maybe plane or maybe three-dimensional space, and then we have to find out those vectors that will span this given subspace. Okay, so we will see the example, right? So this is an example of a subspace, and those examples that are not satisfying the subspace. So subspace by default should contain zero vector or origin all the time. So in this case, when considering this a single line that does not pass through the origin, that is not the subspace. Okay, because subspace by default should contain zero vector. And also, yes, so that was the first condition, right? But this condition is already covered by the closedness under the linear combinations, because given any vectors, and then if you consider the linear combinations of these vectors, and then you freely just set linear combination coefficient as 0, and then we can easily create a zero vector, right? And so being closed under the linear combination should contain zero vectors by default. Okay, so the first condition is actually included in the second and the third condition. Okay, so in this case, because it is not containing the zero vector, so it is not a subspace, right? Then as a special case, there is a smallest subspace, although let's see. We do not usually consider this empty set of vectors, because we have no vectors to choose from to consider their linear combinations, right? So we at least consider the set of the vectors containing at least one vectors, and the smallest vector set that satisfies this closedness under the linear combination is just a 0. So for example, in the case of R3, and then this, the vector set containing only the zero vector, this is a subspace. Okay, because we choose this one vector, and then freely generate any of the linear combination of it by changing the linear combination coefficient, and then it will produce zero vectors, and so it is still closed under this linear combination. So this is a called a zero subspace. Okay, and then now related to a given matrix. Suppose in the beginning we are given a particular matrix, okay, and then we can consider its related subspace. Okay, so the first one is called column space. A column space. So the column space is basically the set of all the linear combinations of the columns of a given matrix A. Okay? So that is called a column space. And this column space is denoted as col A, and this column space is actually the subspace that is closed under the linear combinations. Okay? Right, so let me give an example. Let's see. Over here. So suppose we are given this matrix, and what is the column space? The column space is, so we just collect all the columns that we are given in the matrix. So we have 5 columns in total, right? And then we just consider the span of it. Okay? And then that span of all the columns of the given matrix, so that is called column space, and this is closed under the linear combination. So that is a kind of subspace. And why is it satisfying the condition of the subspace? It is because it is represented as the span of some vectors, right? So as we saw in the previous example, over here, so the span of some vectors is always closed under their linear combinations, right? So you can easily understand that this guy, the column space, is the subspace. Okay. And then now there is another subspace related to a given matrix, which is called a null space. Okay, null space. This is a little bit more trickier than the column space. So the null space is all the set of vectors that satisfies this homogeneous linear system. Okay, so yes, the set of all the possible solutions of our homogeneous linear system, and then collecting all the possible solutions, and then that is called a null space of a matrix A. Okay, so that is just a name, but more importantly, this null space, or the set of all the possible solutions of the homogeneous linear system, is actually the subspace, which means it is closed under the linear combinations. Okay, right. Let's let's prove this closeness under the linear combination for the for this null space. Okay, so suppose that null space is called, for example, B. Okay, so B is a set of vectors that satisfies AX is equal to 0. Okay, and then here let's first consider the vector dimension. So what is this subspace included in this high dimensional space? So here, this is our matrix, right? And then what is at least the dimension of our null space solution? The homogeneous linear system solution. So here, so we need five numbers, right? Because A is 3 by 5, right? And then X should be 5-dimensional vector to at least have the solution for this homogeneous linear system, right? So it is like this guy, right? So this is our homogeneous linear system for this example. So at least the solution for this homogeneous linear system is 5-dimensional vector, right? So the null space is basically belonging to the entire 5-dimensional space because it's just a subset of the 5-dimensional vectors, right? Okay, so that's one thing to note. And then also x1 and x2. So this is a 5-dimensional vector that satisfies this guy. Okay, and then obviously we know that the trivial solution will satisfy this homogeneous linear system, which is this guy, right? And then will this matrix have some other solution for this homogeneous linear system? So by the shape of the matrix, which is 3 by 5, so we have a 5 vectors that are living in the 3-dimensional space, right? So how many pivots do we have maximally or at most? Here we have 3 pivots at most, right? And so that means we have at most 3 columns that have the pivots, right? And so at least two of the columns will be the free variable, right? So this, using this matrix, the homogeneous linear system will have the non-trivial solution, right? So we will, we at least guarantee that. Okay, so let's see. The one of the non-homogeneous solution is 1, 2, 3, 4, 5. This is just an example, although this is not a correct homogeneous linear system solution, but maybe suppose we have these elements in our null space, okay? And then because this guy is so easy, so let's just call it as a x3 and x1 and x2. It's just an enumeration difference, okay? Right, and then we know, at least we know ax1 is equal to 0 and ax2 is equal to 0, right? And then we want to prove this set is closed under the linear combination, okay? So suppose we chose x1 and x2 in this manner, and then let's form its linear combination, or cx1 plus dx2 by using the linear combination coefficient of c and d, okay? And then we want to check whether this guy is also included in our subset of the vectors, which is the set of entire solution of the homogeneous linear system. And then we have to check whether this guy works as the solution for this homogeneous linear system, okay? So is it true or not? Okay, so it is true, right? So we can easily rewrite this as c times ax1 plus d times ax2, and then this guy is 0, this guy is 0, right? And so this will always produce 0, right? So in other words, in our null space, or the set of entire solution of the homogeneous linear system, we freely choose any of these 2 solutions and then perform the linear combinations, and then that will be the solution of our homogeneous linear system as well, okay? So that way the null space, or the set of entire solution of homogeneous linear system, is closed under the linear combination. Does it make sense? So that way the null space is also a kind of subspace which satisfies the closeness under the linear combination. Any questions? 알겠죠? 네.
조건 없이 그냥 만약에 셋에 뭐 ULV가 있으면 유형 V 4층 연산으로 만들어진 모든 것은 서브스페이스 안에 들어가는 거죠.
4층 연산이요? 아, 4층 연산.
스칼라베랑
그렇죠. 네, 리니어 컨비네이션.
무조건 무조건 조건 없이 다 서비스 베이스 하는 그런.
그 셋 안에 들어가 있어야지 되죠. 네. 네. 근데 문제는 까먹었는데 옛날에 뭐 그런 거 좀 해봤는지 모르겠네요. 곱셈과 뭐 나눗셈에 닫혀있다 이렇게 했을 때 뭐 너무 쉬운 거긴 한데 1과 마이너스 1 뭐 이런 게 있으면 일단 이거는 곱셈이나 나눗셈에 닫혀 있죠. So this is closed under the multiplication and division, right? So you choose any of the two and then perform these operations, and then it will be also inside of this guy. But in general, suppose it is suppose we want to make it closed under the addition, and then what other element should we include in our set? Suppose we choose those two and then perform the addition, and then it should include 0, right? And then let's say we just chose these two times. I mean the same thing 2 times, and then perform the addition, and then we have to include 2, right? And also because this guy is also inside of our set, and so we have a freedom to choose this guy as well. And so if we choose this guy and this guy, and then perform the addition, and then 3 should also be included, right? So when will this process end? Okay, so at least in order to make it closed under the addition, for example, and then at least we will need infinitely many elements in this set, right? But in this case, we can just stop at the entire set of the integers, because it already have this negative numbers, right? But we gradually grow or expand our set to make this to maintain this closeness under this defined operations that we consider. Okay, but it will end at a particular point, right? So you can think of the same situation. So that is like this kind of example. Suppose we start with these 3 vectors, right? And these are finite number of vectors, and then we keep adding any of their linear combinations. Okay, and then of course we understand that this set should include infinitely many number of elements, right? But at least can we, or is it possible to represent this set? I mean the set containing infinitely possible linear combination results by using any of the elements in our set. Okay, so it will end at a particular point, and that set will not be an entire 3-dimensional space. So that will only finish or end at the span of, for example, these 2 vectors, right? Any other vectors that are not in the span of these 2 vectors will not be included in this set. Okay, even after we just grow this set infinitely to an infinitely large set. Okay. Okay, so we studied that this null space is also satisfying this closeness under the linear combination. But here, related to a matrix, we studied this column space and the null space. But at least these 2 sets are belonging to a different dimensional space. So in the case of a column space, for example, in this case, the column space belongs to R3. And so A is 3 by 5 matrix, and then the column space is belonging to R3, and null space O1A is belonging to R4. 5. Okay. Okay, and then we studied about these two subspaces related to a given matrix. And then now let's study another notion related to the subspace, which is called a basis. Okay, basis. Okay, so the initial situation is that we are given a particular subspace, whether it is a plane or the three-dimensional space or any kind of subset of the vectors closed under the linear combinations. Okay, and then as I mentioned, that subspace will always be represented as some span of some vectors. Okay, and then those vectors, I mean, if we can find these vectors, then these vectors are called a basis of the subspace. Okay, but here, in order to call these vectors as a basis, and then there is a one additional condition to satisfy, which is we do not allow the redundancies. Okay, so what I mean by that is okay, so in this simple example, so suppose we infinitely grow our set, okay, until it is closed under the linear combinations. Okay, right, and then it will be represented as the span of these two, right? So these two vectors are called a basis of the subspace. Okay, but what about this? So the span of these three vectors, where the third one is already a linear combination of the first two. In this case, let's consider the span of 1, 2, 3 and 2, 3, 4. So in this case, these two sets of the spans, I mean set of the above three vectors and these two vectors will be the same, right? So why is it so? So 1, 2, 3 and 2, 3, 4 having a different directions, okay? And then their span will be this plane, right, containing these two lines. But here the third vector of 3, 5, 7 is already included in our span, right? So even if we consider the linear combination of all these three vectors, so that will remain as just the same plane containing the first two vectors, right? So in order to form this given plane, I mean, when considering this subspace, we are initially given a particular plane, for example, okay, and then we consider the base vectors or ingredient vectors that can span the given plane, and we just need the two vectors, the first two vectors, but not the third one, because third one doesn't play a role of forming or giving the additional kind of dimensions or additional it doesn't increase our span, right? So the first two will be just enough or sufficient, right? So that kind of relationship is is considered as a linear independence among our vectors. So this guy is the redundant one, or that is a kind of surplus, right? That doesn't have any effect of really actually increasing the subspace or the span of our vectors, right? Because that is already linearly dependent of the first two vectors, right? So in this case, even if we remove it, and then the we can create the exact same subspace, right? And so the basis, when talking about the basis of a given subspace, then this basis should contain contain no redundancies. Okay, so we don't allow any of these linearly dependent vectors. Okay, so that is additional condition to satisfy in order to call a set of vectors as a basis for a given subspace. Okay, and then those basis vectors should always be linearly independent. Right? So that is the definition of this basis. So basis is the set of vectors that fully spans the given subspace H. Okay?
베이시스가 여러 개 있으면 여러 개 있겠네요. 다 다른
네, 그렇죠. 그 우리가 또 이야기를 또 할 거예요. 네, 그것도 중요한 포인트죠. 네, okay. So using the basis vectors, we have to fully span the given subspace, but we cannot. We cannot make the span of these bases bigger than the given subspace. We have to exactly match the given subspace, okay? And then they should be linearly independent, which means we don't allow any redundancies, okay? Right? And then let's think of the basis of this given subspace. So here, although we formed this blue plane by the span of these two vectors v1 and v2, right? But let's just forget about v1 and v2, and then let's just consider this plane, okay? Just a plane, okay? So that is initial information that we start with, okay? So that is a subspace closed under the linear combination, and then our task is to find the basis of this given subspace, okay? And the basis vectors should fully span the given subspace, and then they have to be linearly independent, right? So they have to satisfy these two conditions. And then again, let's just forget about this v1 and v2, okay? And then the one example of our basis will be first one and the second one, right? So considering the span of these two vectors, they will form the exact same subspace or plane, right? And then they are linearly independent. And what about another set of basis vectors, such as maybe this guy and maybe this guy, okay? So that will form the exact same plane, right? And then they are linearly independent, right? So as we can see over here, given the same subspace, the basis is not determined uniquely. So basis can, infinitely many possible bases exist, right? But what is unique or what is not changed in this case? The number of bases is will remain the same, right? Given the particular subspace, right? So how many number of bases for many different versions of the basis vectors for a given same subspace? I mean, it will always be 2, right? So we will always need 2 vectors to span the given subspace, and those vectors should be linearly independent. And then the number of basis vectors will remain always the same, okay? So that number, for a given subspace, the number of basis vectors, even though the basis vectors may vary, the number of basis vectors should always be the same, and that number is called a dimension of a subspace. See. Where is the definition of the dimensions? Yeah, so we will see the definition of the dimension in a later slide. But the yeah, as we discussed just now, the dimension is defined as the number of bases for a given subspace. But yeah, we already used the term dimension previously in many different cases. So for example, suppose we are given maybe 1, 3, 5. So this is called a three-dimensional vector, right? Three-dimensional vector. So why is it called a three-dimensional vector? And here we also use the dimension to simply indicate the number of elements in our vector, right? But now the new definition that we discussed about the term dimension is the number of basis vectors in a given subspace, right? And so these two are actually related to each other. So let me explain it right now. So yeah, let's think of R3 as an entire three-dimensional space. Okay, so let me ask the question of whether R3 is a subspace or not. So the entire set of all the possible three-dimensional vectors. Okay, so that is the entire set. Is it closed under the linear combinations? It is closed under the linear combinations because you freely choose any of the three-dimensional vectors and then generate the linear combinations of it, and then that will also be a three-dimensional vector, right? So R3 by definition will include the entire, all the possible three-dimensional vectors, right? So that is trivially closed under the linear combinations, right? Right, and then let's consider its basis, okay, by viewing it as a particular subspace. And then the most simplest form of the basis vector, what is the definition of the basis? So they should be linearly independent, and then they should fully span the given subspace, right? And then suppose there is an origin over here, and then maybe these three vectors will work as the basis. They are linearly independent, right? The first one and the second one and the third one, any of them is not included in the span of the previous vectors, right? And also they fully span the entire three-dimensional space, right? So they are valid basis of R3, right? But there, we can also think of really simplest, probably the most simple, the simplest form of a basis, which is 1, 0, 0 and 0, 1, 0 and 0, 0, 1, right? So in this particular version of the basis, they have the length of 1. Okay, although we didn't formally study or formally discuss about the definition of the vector length or the length of the vectors, but yeah, you guys know the length of the vectors, right? As like 1 squared, 0 squared, and 0 squared, and take the square root of it. So this is the definition of the length of the vectors, right? Based on the Pythagorean theorem. But anyways, each of these three vectors will have the length of 1, which is kind of simple, right? And then they have the angles between any pair of the two vectors as 90 degrees, right? So they have 90-degree angles for any given two vectors, right? So this is probably the most simplest vector, and they are linearly independent as well. They fully span the three-dimensional space, and then they are linearly independent as well, because here we have the first one and then the second one. Can we represent this guy as the linear combination of this guy? It is not. Why is it so? So we have 1 here. So let's try to make the second vector as a linear combination of the first one. And then using some linear combination coefficient. But here we always with 0 over here. So by multiplying any values with this 0, we will just obtain 0, although we have to obtain 1 over here, right? And so these two are linearly independent. And likewise, suppose, let's try to make the third one as a linear combination of the previous two, and then these two vectors have zeros on the third element, and so by using the linear combination of these two, and then we will always obtain 0, but we have 1 over here, and so we cannot make the third vectors at all, right? So they are easily, linearly independent, right? Okay, then let's see. Okay, so and then now any three-dimensional vector is included in our subspace, right? And then we obtained one version of the basis vectors of our subspace, right? And then we chose a vector from our subspace, and then we have a set of vectors that fully spans the subspace. So we chose such a vector, and then we should, it is guaranteed that we can always represent this vector as a linear combination of our basis vectors, because by definition this vector is inside or chosen from this set, right? And then these vectors will fully span our subspace, right? So we have a capability to represent any of the vectors in this subspace as a linear combination of these basis vectors. And also, furthermore, these vectors are linearly independent, right? And this guy is belonging to the span of these three vectors, and these three vectors are linearly independent, right? And then can we obtain these C1, C2, and C3? Does the solution for this C1, C2, and C3 exist? It exists, right? And how many solutions will exist? Infinitely many? 네, 여기서. So there will be, we will only have one solution because these vectors are linearly independent, right? So, this is quite important because we will use it in the later chapters. But by using the basis, once we obtain the basis of a subspace, okay, and then we choose any vector from that subspace, and then that vector is always represented as a linear combinations by using our basis vectors, and that linear combination representation will be always unique by the fact that these bases are linearly independent. Okay, so there are these general characteristics, and then now what is what is simply the solution for C1, C2, and C3 in this case? We have 1, 3, 5 as a vector, and then our basis vector is really the simplest form of 1, 0, 0, and 0, 1, 0, and 0, 0, 1, and the solution will be 1, 3, and 5, right? So in this case, we can consider, for example, Rn as an entire space of an Rn as a particular subspace, and then if we consider it's the simplest form of a basis, which is called the standard basis, which is represented as a 1, 0, 0, 0, and 0, 1, 0, 0, 0, and so on, all the way to the 0, 0, 0, 0, and 1. Okay, and then any vectors will be represented as a linear combination of these basis vectors, and then we can easily see that the number of basis vectors in this entire Rn when considering this simplest form called the standard basis, and then the number of basis vectors will be the same, simply the same as the number of dimensions or the number of elements, right? And so that's that's how we relate this simple notion of the count or the number of elements in our n-dimensional vector, as really the n-dimensional kind of subspace, which has the basis, the number of basis vectors as n, okay, for the entire Rn, as a particular subspace. Any questions? Okay, then let's take a break for 10 minutes and resume at 1:05.
연재가 되니까 이걸 다 할지 안 해야 되는 걸 다 여기 이거 왜 지금 배우시는 거예요? 다음 서버 스페이스가 뭐 서버 스페이스랑 스펜이랑 왜 스펜이랑 안 한다는 말은 스페이스랑 동사야. 생산하냐? 기습기 받으려고. 명사로도 들이 있어. 보통 근데 스펜 하면 막 스펜 한다고 하더라고. 우리가 스펜 한다고 하면 기성 한다. 뭐? 그래서 그 문제가 휴진 공전 기저 벡터는 기저 벡터 세트는 엄청 많다고. 그래서 이런 게 있었어. X3이 있는데 얘네는 그 R3에 기저 벡터 있다라고 이렇게 느껴졌는데 우리가 그걸 확인했거든. 맞아. 세 개로 3부분이 4인 중에
물론 보기를 하려면 저희가 그리고 PhD도 지금 디자인을 좀 하니까 CSS를 하나도 안 쓰고 그거 아니지 않겠지? 이거 CSS 하나도 안 쓰고 그냥 이걸 많이 그냥 기능만 하면 돼. 그래서 내가 물어봤어. 디자인 중요해요? 반대 행복을 이해해야 번 눌러보세요. 보안 신경 써야 되나요? 할거 없다 되나요? 여기 두 번째 물론 비밀번호 SDK 지원했다는 스페이스인데요. 제대로 케이스를 SDK 집어넣어서 나는 그거를 프로 몇 점씩이 아니라
저 거짓말하고 있어.
내가 약간 코딩 사이즈 데이터베이스도 PHP 많이 그 헤드라인도 5월 10일 아침도 오늘은 살짝 할때 그냥 아침으로 사원으로 놀러 가요. 그냥 매일 베이직 써요. 여기 근데 화가 이번에 말을 나는 기억이 안 나는데 교환으로 윙
아니 시용이 보내.
그냥 5월 6일 학교 쉬냐? 쉬어? 5월 6일 5월 6일 쉬어? 아이도 쉬어. 민규 매일 온 거.
Okay, let's continue. Right, then let's look at this example again. In order to find the basis vector for the null space of a given matrix. Okay, so we are given this matrix, and then we know the definition of the null space, right? And then we prove that the null space is satisfying the linear closedness under the linear combination, right? And then now, although we didn't prove, I mentioned that the subspace is always represented as a span of some linearly independent vectors, and those vectors are called a basis vectors, right? So this is kind of an overall story that we discussed in the previous lecture, right? And then now let's look into this particular example and then find out what the basis vectors are for the null space of a matrix. Okay, so using this matrix and then performing the Gaussian elimination of the first phase to obtain the echelon form. Okay, so this is this is a reduced echelon form, right? So once we obtain the reduced echelon form of this matrix, then we basically represent it. I mean, the solution for this homogeneous linear system, where we set the B part as 0, and then represent the solution as a parametric vector form, right? And then from here, x1 is represented as 2 times x2 plus 1 times x4 and negative 3 times x5. Does it make sense? Okay, so what is the basic variables? So those two are basic variables. So for those two basic variables, we represent them with respect to free variables, right? And then for the free variables, we just simply just write the free variables as it is, because they are really the free ones that we can independently choose any values for, right? Okay, and then the next trick that we apply here is to extract out or factorize the free variable, by using by leaving some constant vectors associated with each of our free variables. So yep, so x2 is involved over here and over here, right? And so 2 and 1 and 0, 0, 0, and x4, which is our another free variable, is multiplied with the 1 times, yeah. So for this part, yeah, for the other free variables, it will only contain that free variable itself, so it will not contain any other free variables, right? So in the place of other free variables, you will have zeros, and then -2 over here, and 1 over here. So you guys know how to factorize the, or obtain this factorized form. So this is called the parametric vector form, right? All right, and then at least, yeah, this is our representation of the null space or the solution for the homogeneous linear system. Okay, and then x2, 4, 5 are the free variables, right, associated with the specific vectors. And in this example, yeah, the null space or the solution for homogeneous linear system is a 5-dimensional vectors, right? And then we have the 5-dimensional vectors, and this, yeah, we can at least understand that it is represented as the span of these 3 vectors, right? So again, this is subspace, and this is spanned by some vectors, right? And then now, here the problem is we have to obtain the basis for this null space, and then at least this any possible homogeneous linear system solution is spanned by these 3 vectors. And then can we say these 3 vectors are basis for the null space? Yes. So there are 2 conditions to satisfy as a basis vectors. The first one is fully spanning the given subspace, and the second one is linear independence. So are these 3 vectors linearly independent? Can we guarantee that? How?
첫 번째 거에는 두 번째 1이 있고 두 번째 거에는 네 번째 1이 있으면 서로 만들 수 없어.
네. 똑똑한데요. 이렇게 바로 나올 줄이야. 이거를 항상 그렇다고 얘기할 수 있을까요? 그러니까 어떤 매트릭스 A가 주어져도
네, 항상 그럴 것 같아요. 예. 왜냐하면은 프리 베리어블이 있으니까 프리 베리어블만 1이 지키잖아요, 그러면.
네.
그러니까 그 부분에 뒤에는 0, 다 0이고.
네. 그래서 보자. 내가 생각한 것보다도 쉽게 생각한 것 같습니다. 자, 일단 요거 요놈들 때문에 그렇다는 거죠.
그 양력분 다 0밖에 나올 수 있어요.
그러네요. Okay, so the student gave the really awesome answer here. Okay, so the point is, for each of our free variable over here, 2, 4, 5, okay, so they will be just written in its only variable, right, by itself, without involving any other variables, right? And so even after we obtain this factorized form, okay, and then so this is associated with x2 and x4 and x5, which will work as a linear combination coefficient, right? But here, in order to check whether they are linearly independent or not, so here we have only one in this place, in the place of the second variable, but all the other parts, okay, so basically this guy, x2 itself, will not contain any other free variables, right? So these will be zeros, and those parts will also be 0, and this part will also be 0, right? So similar to like this example. Okay, this example. So we have non-zero in this second dimension, but this guy has a zero value in the corresponding dimension, so it is impossible to obtain or represent this second vector by using the linear combination of the first vector. And likewise, we have non-zero value in the third dimension, but the previous two vectors that we can use to form the linear combination, they will have zero values in the corresponding dimension. So yeah, we have, it is impossible to obtain the linear combination by using them to obtain the third one, right? Similarly, yeah, in order to represent any of these vectors, any of the single vectors, by using the linear combination of the other vectors, so we can see that, yeah, it is always impossible to represent any of these single vectors with respect to the linear combination of the other vectors. So that way we can easily understand that these vectors will always be linearly independent, right? And so those vectors will be the basis of our null space. Okay? All right, and then before moving to the next example, let's also think of the column space of this matrix. So again, the column space by definition is the span of these 5 columns, right? And then what will be the basis of this column space? So because it has this reduced echelon form, okay, so we can indicate the which one is a free variable and which one is the basic variable, right? So this guy is a basic, yeah, so basic free, right? So BF, F, right? And then also in this case, so from this pattern, we can see that each of these free variables and their corresponding columns will be represented as the linear combinations of the previous columns. Okay, so when studying the linear independence or dependence, the first one and the second one and the third one and so on, by adding one vector at a time, if one that vector is represented as a linear combination of the previous ones, and then that's when the entire the set of the vectors are linearly independent, right? But given this set of column vectors in a matrix, yeah, we can imagine the same scenario of adding one vector at a time, and then the basic variables and free variables are obtained from the pattern of the pivot, from the pivot position in our reduced echelon form or echelon form, right? And here, yeah, related to this the strategy of checking whether they are linearly independent or dependent. Okay, so those free variables and their corresponding columns will be represented as a linear combination of the previous vectors. Okay, so yeah, let's understand why. Right, so yeah, we will see the example in the next slide as well, but here okay, so this is our homogeneous linear system, which is converted into this reduced echelon form, and these two matrices are row equivalent, right? So let's call this original matrix as an A, and this matrix as B. Okay, so originally we are given this matrix AX is equal to B, and bx is equal to b, where b is the reduced echelon form of our original matrix A. Okay, and then the solution set of ax is equal to 0 and bx is equal to 0, they are the same, right? Because row reduction or row operation will maintain or will keep the entire solution set as it is or the same, right? Because that's how we can apply the row reduction to obtain the solution of the original linear system, right? Okay, and then now let's consider this homogeneous version of the linear system. And then, yeah, again, as I mentioned, the solution for bx is equal to 0 is the same as the solution of ax is equal to 0. And let's look at the pattern of b. Okay. So bf, bf, f. All right, we have to make 0 vectors. And then let's just devise some possible linear combination coefficient to make 0 vectors. Okay, so here, so we have 5 different columns, and let's consider their vector equation form, and then we can just simply set the 0 linear combination coefficient for the 3rd, 4th, and the 5th columns. And then let's just try out applying or assigning non-zero linear combination coefficient. Okay, so here, because this is our free variable, it doesn't have any pivots, so it doesn't have any non-zero entries that have the 0 entries in the first column, right? And so in this case, oops, in this case, we have 1 over here and negative 2 over here. And then how can we assign the linear combination coefficient to make their sum as 0? So simply, yeah, so I'm running out of the space, but yeah, let's just multiply the first column by 2 and then multiply the second column by 1. Okay, because we see 1 and negative 2 over here, and then 1 0 0 times 2 and negative 2 0 0 times 1. Okay, so that will cancel out each other, and so we can maintain the 0 vectors. And then the 3rd, 4th, and 5th will be will have the linear combination coefficient as 0, right? So by only using the first and the second one, yeah, we obtain the linear combination, I mean the solution for homogeneous linear system. Does it make sense? So 2 times b1, where b1 is the first column of b, which is our reduced echelon form, and b2 is equal to 0, right? So it doesn't involve any other b3, b4, and b5. And from here, what is b2? It is negative 2 times b1, right? And so we obtained the representation of b2 as a linear combination of the previous column b1, right? So at least in this particular example, the first free variable, which is the second variable, okay, so that is represented as a linear combination of the previous one. Okay, and then let's try to represent the linear combination of the first and the second columns for the third one, which is one of our basic variable. Is it possible by just setting it as maybe 1, which is non-zero coefficient on this column, and then yeah, can we represent it? I mean, by setting the linear combination coefficient as 0 for the 4th and the 5th one, and then can we set any of the linear combination coefficient for the first and the second one to make the entire column combination of the 3 as 0? It is impossible because we have 1 over here, which is the first non-zero entry in that dimension, right? That was not found in the previous columns because we all have zeros over here, right? So once we set the linear combination coefficient for this basic variables column as non-zero, and then we cannot make this non-zero entry as 1 by using any of the linear combination of the previous one, right? Because the pivot is, by definition, the first non-zero entry, right? So again, we are considering the strategy of adding one vector at a time and checking whether that vector is represented as a linear combination of the previous ones, okay? But here the point is, we are doing that thing, we are doing this kind of process on this reduced echelon form, not from the first, the initial form, because two solutions of ax is equal to b and bx is equal to ax is equal to 0 and bx is equal to 0, they will maintain the same, exact same solution set, okay? So this form is much easier form, easier representation to think of the solution. Whether the solution is possible or not. Okay. Okay. Then now let's move to the fourth one, which is a second free variable, and then maybe let's assign the linear combination coefficient as 1. Okay. And then here, from the definition of the reduced echelon form, I guess it is getting messier, but we will have the columns like columns of having 1 only in the pivot position and 0 on other dimensions, right? And then for this free variable, which doesn't have any additional non-zeros up to that pivot position, and then from here, for -1, we can simply make that -1 by just multiplying the first row by 1. And this guy can be created by just multiplying this guy by -2, right? Because we already have really simple form of a vector of 0, 1, 0, 1, 0, 0, 0, and 0, 1, 0, 0, 0, right? And then the free variable doesn't exceed or doesn't have any non-zero elements beyond the vectors that we already found as a really simple vector of the vector that have only one non-zero entry. So here the point is, those columns corresponding to the free variable can be created or it can be represented as a linear combination of the previous ones, basic variables, okay, or the columns corresponding to the basic variables. Right. And so in this case again, when considering this homogeneous linear system solution, and then by looking at the pattern of -1 and 1, and then minus b1 plus this guy, no, it should be plus b1 to cancel out this -1, and by using this guy and -2 times b3 and plus b4 should be 0, right? So this is how we easily manipulate or obtain this equation. So what we did was simply set this guy by the linear combination coefficient for this guy corresponding to the free variable as 1, okay, and then we just find out some corresponding values as a linear combination coefficient for the previously found basic variable, okay, and then we can easily make this equation, okay. So that is our one of the solution for the free variable. And here the point is, so b1, b2, and so on are the columns of B, right? But this solution, what is the solution? So 1 and 0 for the b2, right? And -2 for b3, and 1 for b4, and 0 for b5. Okay, So that linear combination coefficient corresponding to the columns of B is satisfying our homogeneous linear system, right? And that linear combination coefficient will also be the solution for AX is equal to 0. So what does that mean? Even before checking whether it is true or not, let's use A1, A2, A3, and A4, A5 as our original column. Okay, original column. And still, replacing those guys, B1, B3, B4 with A1, A3, A4. Still the solution will hold or will be true. So plus 1 times A1 plus negative 2 times A3 plus A4 is equal to 0, right? So you can easily check that out. So this guy is this guy times 1 and this guy times negative 2, okay, and plus, and then it will make 0, okay. Any questions? Right, so in this manner, the linear independence or dependence, and I mean how we check whether the set, the vector set is linear independent or dependent, is really, I mean, closely related to the basic and the free variables. Okay, so in summary, the free variables will be represented as a linear combination of the previous columns. I mean, the free variables column is represented as the previously found basic variables, which means that column corresponding to the free variable will be included in the span of the previous ones. Okay, so that guy is the one that makes this set linearly dependent. Okay. All right. And then let's look at the related problem of finding out the basis vector for the column space of this matrix. Okay, so now, I mean, in the previous example of this question or this problem, we obtained the basis for the null space. Okay, again, the basis for the null space, and then now, what is the basis for our column space? So again, the definition of the column space is the span of the 5 columns, right? And then what could be our basis for the column space? I mean, so, right, the pivot columns will be our basis vectors for the column space. Okay, so again, the span of the 5 column vectors will be the same as the span of only the 2 vectors that are linearly independent, or the columns corresponding to the basic variables. Okay, and they are linearly independent, right? So that's how we can call it as a basis, right? Any questions? Right, and then this is the simple but quite important theorem that will appear in the next chapter. But because we discussed this in detail, so let me just discuss about this theorem called rank theorem. So here, what will be the dimension of the column space? So what is the basis of the column space? I mean, there could be many different versions of the basis vectors for the column space, but what will be the number of basis vectors for the column space? It will be 2, right? So what is the 2? 2 is the number of free variables that we obtain, right? The number of free variables is the dimension of the column space, right? And then now let's consider the dimension of the null space. So null space. So the null space dimension, right? So here, so although we do not know the particular basis vector for the null space, but at least we can say the number of basis vectors that we will obtain for the null space. which is the number of free variables, right? For each free variable, we will have one particular vector associated with it. And we can see, yeah, we already understood that they are linearly independent with each other, right? And so the number of free variables is the number of, the dimension of the null space. Okay? So again, in summary, the number of basic variables is the dimension of the column space, and the number of free variables is the dimension of the null space, right? And then now, what will be the sum? Okay, so in this case, yeah. So we have 5 columns in total in this matrix. Okay, in m by n matrix, we have n columns. This is an obvious, right? So among n columns, each column will be either free or basic variables, right? And then the number of basic variables is the dimension of the column space, and the number of free variable is the dimension of the null space, right? And if we sum them up, the dimension of the column space and the null space, and then that sum will always be the number of columns in our matrix. So in this case, 5. Okay, so that is called where is 2.9? Okay, so that is called a rank theorem. We haven't studied the term rank, but this the meaning of the rank is, the definition of the rank is the dimension of the column space. Okay, so that is called a matrix rank. Okay, so again, the definition of the term rank is the dimension of the column space of an A. Okay, right, and then this guy is the number of what? Basic variables, right? That is the rank, right? And also the null space of an A and its dimension once we add them together, and then given m by n matrix where we have n different columns in total, okay, and their sum will always be n. Any questions so far? Okay. Let's see. And then, let me briefly go through the next example that I think we already explained or already discussed. So this guy is actually the reduced echelon form of the of some matrix. Okay, so some matrix is this guy. So consider this matrix initially, and then its reduced echelon form is this guy. Okay, and here we can easily see that this is basic, free, basic, right? Okay, once finding out which one is basic and which other ones are free variables, and then in this case, what is the basis? Okay, basis for the column space. So the basis is this guy, and this guy, right? But what about this guy? So in this case, so we first form or obtain the reduced echelon form, okay, and then in the reduced echelon form, the reduced echelon form is actually this guy. This is how these examples are designed. But B, B, F, F, and B, 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 F, F, and B, and then here, what will be the basis for the column space of the matrix A. So once we identified which columns are basic variables, okay, and then in order to obtain the basis of the column space, we have to bring those columns from the original matrix, right? So it is obvious, right? So again, the column space will be the span of, by definition, the span of the 5 different columns, right? And then from this pattern B, B, F, F, and B, which is obtained from this reduced echelon form, we can easily see that the third one is represented as the linear combination of the previous two, right? And then that relationship was obtained from this reduced echelon form, but due to the fact that they are row equivalent, or they are equivalent linear system having the same solution set, right? And so in this considering this a homogeneous linear system, and then B3 plus this relationship can be easily obtained, right? And then we just replace those B1, B2, and B3 with A1 and A2, A3 respectively. That will still be the solution for the original homogeneous linear system, right? So -3 and 2, we can easily verify that by multiplying -3 and by 2, right? So 1 times -3 and 3 times 2 and 6, and then we will obtain 3, right? And so magically this solution will the solution obtained from this reduced echelon form will be the solution for Ax is equal to 0, right? So here the answer is these 3 columns, right? And if this problem is asking the dimension of this column space, and then the dimension will be 3, right? Because we have 3 free variables, and although we didn't obtain yet, but the dimension of the null space will be 2. 5 by 5 minus 3, which is 2. Any questions so far? Okay, then so this is an obvious one that we already understood. The pivot columns of a matrix is the basis for the column space of an A, right? Okay, and then let's move to the chapter 2.9. So in this chapter, the main part, or the important part, is the coordinate system. Coordinate system with respect to, or relative to, a particular given basis B. Okay. All right. Right. Let's think of V1 as 1, 2, 3, and V2 as 2, 3, 4. Okay, and then what will be this corresponding point? Right, this guy, right? And then let's just compute it. 오, 일단 보죠. 3, 2, 6, 8, 4, 2, 8. Right? So I just multiplied by 2 and then added it with the first one. Okay? And then how did we obtain this linear combination coefficient as 2 and 1? It is because we have this parallelogram pattern, right? So V1 times 1 and V2 times 2, right? So this is the force or the vertex of our parallelogram obtained in this manner, right? Right. And then certainly this point is inside of the subspace H spanned by V1 and V2, right? And then now let's consider its linear combination coefficient. Let's see. So what are the numbers corresponding to this question marks? It is 1 and 2, because that's how we obtained this guy, right? And then now let me give another vector inside of our subspace H, okay, as maybe this guy. And this guy, yeah, I'm gonna say that this guy is also chosen from our subspace H, which means it is at least represented as our basis vector, which are linearly independent as well. Okay, and then how can we obtain these two values? We will just solve the Ax is equal to b, right? So this is nothing but a vector equation form where we have two columns as our basis for the subspace, and then the given vector, which is inside of our subspace, right? Okay, and then we know how we can obtain these two linear combination coefficient. Okay, we will just do the row reduction and then obtain the corresponding solution, right? And its actual solution is 1 and 5. 네? 네, 그러네요. 5 and 1. Okay, because I created that way by having those linear combination coefficients in my mind. Okay, but anyways, we know how to obtain that solution by just doing the Gaussian elimination or row reduction, right? Right, and then this 5, 1. I mean, where will that point be placed? Yeah, let's say it is 3, 1. Okay, because it's just an outside of our plane, but 3, 1 is over here, right? 3, 1 is over here, right? So in this case, yeah, so this is a weird looking B. Suppose it is 1, 2, 3, 2, 3, 4, and then yeah, let's use this guy, 5, 8, 11. Okay, so that is having the linear combination coefficient as 1 and 2, right, from this shape of the parallelogram, and this guy is represented as some weird shape. Okay, so this guy 1 and 2, or 1, 2, is called a coordinate. Okay, coordinate relative to this particular basis in our subspace H, or spanned by our basis. Does it make sense? So again, we consider some subspace H and its basis vector, which is fully spanning the given subspace and are linearly independent. Okay, and then we choose particular point from our subspace. Okay, so it can be this point, or it can be even like this point or that point, and so on. Okay, so we choose any vector or any point from our subspace. Okay, and then that point will be represented as a linear combination of our basis vector and that linear combination coefficient with respect to our basis vector. I mean, those linear combination coefficients will always be unique for a particular vector, right? Because the basis vectors are linearly independent, right? And then those linear combination coefficients 1, 2, okay? And for example 7, 13, 19 is like, what was that? It was 5 and 1 and B, right? Okay, so this is called a coordinate relative to our basis, and these are really the coordinate. Okay, coordinate, yeah. 그러니까 한국말로 코디네이트 뭐죠? 좌표값이란 뜻이잖아요. 이게 진짜 좌표값이란 뜻이고요. 그 좌표값에서 각각의 축의 1,0과 0,1을 뭘로 쓰는 거냐면 바로 여기서의 요 벡터를 1,0로 쓰고 요 벡터를 이제 0,1로 썼을 때 요 각각의 점들의 이 지금 공간상에서 새로 이게 하여튼 지금 3차원 공간 안에 인베디드 되어져 있지만 어쨌건 सब스페이스, 그리고 그 सब스페이스의 베이시스는 2개. 그러니까 실 차원은 2잖아요. 그러니까 실 차원으로 볼 때 그것들을 가지고 이런 평행사변형 꼴로 만들어지는 좌표값을 생각할 수가 있잖아요. 그 좌표값이 바로 저 리니어 컨비네이션 코에피션트를 우리가 뭐 리니어 시스템을 풀긴 해야 돼요. 그렇지만 그렇게 해서 얻어지는. Okay? And then yeah, let me add one more explanation about this. So we understand that the basis is not unique for a given subspace. So how about having the basis for maybe maybe this guy and this guy, and then using the same point of 5, 8, 11, it may have a like different coordinate value, so which seem to be like 0.4, and then let's see, it's like a 1.9 for example. Okay, so that will be the coordinate relative to another basis using v1 and v2. Okay, but those 2 points, okay, are really the same point of 5, 8, 11 for example. Okay, so that point can be represented as a different coordinate vector relative to different basis vector, even for I mean even when representing the same point. Okay, all right, and that's it for today. So let's continue this Wednesday. 네.
여기서 널 스페이스의 디멘전이란 이 포함되는 디멘전과 다른 그 최소 이 성분 베이시스 개수를 말하는 거죠.
디멘전이요? 네.
이거랑 다른 게
그거랑 다른 거예요. 그러니까 이거는 뭐냐면 일단은 5차원 벡터다라는 의미예요.
네.
그 엘리먼트가 5개짜리의
네.
벡터 공간에 있는 어떤 부분 집합이다라는 뜻이 되거든요.
네.
네.
그리고 그 지금 이거를 한 이유가 이게 베이직 얘네들이 앞에 거에 그걸로 표현할 수가 있어가지고
네.
그래서 그거의 뜻이
네.
잠깐만요. 그래서
네. 네. 그러니까 우리가 그 아까 그 5개짜리 컬럼의 베이스 그 컬럼 스페이스 좀 너무 지저분해지긴 했지만
네.
지금 요 5개의 컬럼이 있는
네.
매트릭스의 컬럼 스페이스 그리고
네.
그거의 베이시스를 구하려고 하는데 이 5개 일단은 스팬으로 정의되는 것이 컬럼 스페이스인 건 맞아요.
네.
그렇지만 이게 지금 5개 벡터가 있긴 한데
네.
이 중에 우리가 이 서브스페이스의
네.
베이시스를 따지려면 이 중에 이제 우리는
네.
그 리니얼 인디펜던트한 걸 뽑아야
네.
되잖아요. 그러면 리니얼 인디펜던트한 거는 이제 하나씩 추가를 하면서
네.
어느 누군가가 그 전에 거에 포함이 되는지를 체크를
네.
하면 되는데
네.
그게 이제 그걸 어떻게 실제로 체크를 해야 될지.
근데 이게 프리들은 앞에 베이직으로 할 수 있다는
맞아요.
거죠. 네.
그게 이제 어디서 나왔느냐? 바로 이 reduced echelon 폼을 구하고 나면
네.
그 이제 아까 얘기했던 것처럼 free variable에 해당하는 그 컬럼은
네.
그 앞에 있는 basic variable의 컬럼들로 이제 걔네들의 리니어 컨비네이션으로 다 표현이 되기 때문에
네.
네, 그래서
이게
이제
솔루션 셋이 같아서
그렇죠. 솔루션 셋이 같아서 그런 거예요. 네.
그리고 마지막으로
네.
그 제가 이게 옛날부터 고민이었는데
네.
AX는 0에서
네.
이 AX는 B가
네.
이게 되는 게 있고 그러니까
네.
얘가 해가 존재하면 이걸 평행 이동한 거잖아요.
네.
그래서 이게 왜 되는 게 있고 안 되는 게 있는가 생각을 해봤는데
네.
그게 그래서
네.
이게 오늘 배운 거에서
네.
널 스페이스가
네.
이렇게 이게
스페이스.
널 스페이스가 아니라 컬럼 스페이스죠.
네.
그래서 이 0이라는 놈은 항상 여기 포함되기 때문에
네.
이게 해가 항상 존재하는 거고
네,
B가
그렇죠.
여기 있으면 되고 밖에 있으면 안 되는 건가요? 이게 해가 존재하는 게
지금 이걸 그린 게 뭐죠? 컬럼 스페이스예요?
네.
컬럼 스페이스?
네.
오케이. 네. 오케이. 네. 그렇죠. 컬럼 스페이스가 이렇게 돼 있으면 이 B가 맞아요. 여기 포함이 되어 있으면
네.
네. 그럼 일단 해가 있는 거죠.
네.
해가 있는 건데
네.
우리는 이제 이거의 널 스페이스는 아까 여기서 봤던 것처럼 이런 이제 원래 이제 컬럼 스페이스는 이 5개들의 컬럼 있잖아요. 컬럼의 이제
네.
조합인 건데 지금 요거 이 널 스페이스는 기본적으로는 좀 따로 구해야지 되는 그러니까 reduced echelon 폼을 구하고 파라메트릭
네.
벡터 폼을 구해야만 얻어지는 폼이고요.
네.
네, 그러니까 이제 이런 어떤 뭐 3차원의 어떤 솔루션 스페이스가 있는 건데
네.
일단은 이 B가 지금 여기서 이야기했던 건 이건 컬럼 스페이스고요. 이건 3차원 공간이죠.
네.
그러니까 B도 역시 3차원 공간에 있는 벡터고
네.
그러면 B가 여기에 어딘가에 이제 AX 그러니까 A의 컬럼 스페이스 안에 들어왔으면
네.
솔루션이 있다라는 건데
네.
그 솔루션이 있을 때는
네.
그 솔루션은 바로 어떤 특정한 솔루션 하나가 있고 그 다음엔 이거를 그대로 평행 이동을 한 버전이라는 거죠. 이거를 그러니까 평행 이동은 여기 와서 해야 되는 거예요.
이 따로 솔루션의 공간이 있다는.
네. 그러니까 AX is equal to 0의 솔루션 스페이스는 혹은
네.
솔루션 셋은 이거죠. 지금 5차원 공간에
네.
있는 공간이죠.
네. 네.
근데 지금 이거 그러니까 B가 그러니까 지금 AX is equal to B에서 이게 솔루션이 있는지를 따지는 것은
네.
바로 B가 바로 이 3차원 공간 내에
네.
A가 가지는 3차원짜리 컬럼들의
네.
컬럼 스페이스 있잖아요.
네.
그 컬럼 스페이스 내에 이제 이게 B가 이제 있느냐 없느냐를 따지는 거잖아요.
네.
그래서 그게 이제 그쪽에서 확인이 됐으면
네.
그러니까 B가 이제 이 안에 있으면 그러면 이제 이 어떤 솔루션 스페이스를
네.
이동을 하는 거라는 거죠.
그거를 뭔가 그림으로 표현할 수가 있나요? 이거
그림으로 이게 좀 표현하기가 좀 어려운 것 같아요.
이게 뭔가 연결을 지려고 했는데 너무 따로 노는 것
네,
같아서.
맞아요. 좀 따로 노는 게 있어요. 그러니까 그게 직접적으로 바로 연결이 되지는 않아요.
아 그런가요?
다만 이게 뒤쪽에도 좀 나올 텐데
네.
우리가 나올 텐데 그런 건 있어요. 그러니까 그게 기본적으로 차원, 그러니까 그 서브스페이스의 차원이
네.
서브스페이스의 차원이 아까 그 랭크 티어럼이라고 우리가 배웠듯이 베이직 베리어블이 뭐 이렇게 5개 중에 컬럼이 5개인데 베이직 베리어블이 2개고
네.
혹은 3개다.
네.
그다음엔 프리 베리어블이 2개다라고 하면
네.
하여튼 이 5 디멘전 스페이스 상에 존재하는 널 스페이스는 베이시스 벡터 2개라는 거잖아요.
네네.
네, 그러니까 저쪽에서 베이직 베리어블이 많으면 이쪽은 프리 베리어블이 상대적으로 몇 개 없는 거니까
네.
그렇기 때문에 이쪽의 실 디멘전은 좀 적을 수 있는 거죠. 그런 관계만 있지
네.
어떤 이 직접적으로 뭔가 유도가 되지는 않아요.
표현하기가 힘들다는.
네,
네.
맞아요.
그렇군요. 네. 감사합니다.
네.